So, like that, I said, hey, your volume's low, turn that up. Another trick. All right. So again, this semester, I'm going to go through and start off with uh, general linear model and some correlation stuff. Okay. Um, Everybody here knows what a correlation coefficient is, right? Show of hands. Anybody confused? Not know what a correlation coefficient is? Easy peasy, right? We've all gone through and talked about it. When we actually get into correlation, different things you can go through and do with it, it starts to get a little bit more complicated. Making sure, again, like anything that we do in terms of our tools that we're using, wanting to be very clear on what we can and can't infer from this, and how confident we should be in the precision of our estimates, things along these lines. Okay, so we're going to talk about the general linear model, some basic assumptions, different variations on this before we jump into some correlations. Okay. General linear model, anybody get scared when they hear that? I get a little nervous, right? This is just the mathematical foundation of everything. Everything we done that we did last semester, the general linear model, we just didn't talk about it like that. Okay. So just want to give you some background for when this comes up in papers. You kind of know what this is talking about, and then we'll sort of start to get into some more specific expressions. Okay. So to this point, we have been working on what we might call univariate statistics. Okay, this is one input, one output, one IV, one DV. Although some people get sort of worked up about sort of what an IV and a DV is, things along these lines, right? And this has served us really well. Okay, but we have some problems with our univariate statistics. They can be cumbersome and inefficient. Okay, I'm interested in the relation between gender and college performance. Okay, college performance as a construct could be a lot of different things. How do I go through and measure this, right? I could be quantify this as course load, class attendance, hours study, college GPA, major. There's just a lot of stuff. This is a lot of univariate tests that I'm going through and running. So we can think about this as being somewhat inefficient, right? It would be kind of nice if maybe we can bundle some of this stuff together. Okay. And here's the big thing that I think is kind of the issue. It starts to limit the types of questions that we can ask. Okay. I can ask in a univariate model what the relation between trauma severity is and psychological stress. I can do that, right? I can look at whether or not men and women differ in trauma stress, right? I can look at if there's an association between social support and post-traumatic stress, right? But after a while, this starts to get pretty boring and might not capture the complexity of the types of phenomena we're interested in looking at, right? And so we run into a problem. Our solution here is going to be leveling up into some multivariate statistics. Okay, if we're talking about multivariate statistics, this is a broad class of modeling techniques. And what we can start to do here is we can start to look at sets of variables. Okay, what I can do is I can have multiple predictors and multiple outcomes depending on what model I'm using. What I can do, and this starts to become really cool, I can look at associations between outcome variables to start to increase my power. Okay. We will not talk about MANOVA in here. And MANOVA is something that sort of people used to be jazzed about, sort of less so. William, I know though, in Allison's lab, sometimes you use MANOVA models to look at sort of collections of outcomes, right? And what happens if you have a collection of moderately related outcomes, that MANOVA analysis is more powerful than it would be if you're using individual ANOVAs, right? So there's some ways we can go through and leverage correlations among outcomes to increase the power to detect effects, which can be a very good thing, okay? And here, this is what I think is sort of our greatest strength, is I can start to expand the range complexity of the types of questions that I can be asked, okay? I can do more interesting research if I'm familiar with the types of models out there and how they go through and ask different questions. Half of the papers on my CV are just sort of thinking about like, oh, hey, here's a new model. What would that look like in these data? Do I have data to look at this? Here's just me trying to learn this new model. Oh, that actually kind of turned into a paper. Maybe not half, but sort of a fair amount of them, right? So it allows us, and so this is the benefit of doing this, even if you don't want to be a statistician for the rest of your life, I can't ask questions if I don't know how to ask interesting questions, and sort of being exposed to different types of models opens up ways to say, oh, I wonder what that would look like in my specific area. And then pretty soon you got some pretty interesting stuff. Okay. And so this starts to become, I think, the biggest benefit of multivariate statistics. Okay. So the types of questions I might ask with a basic multivariate model, what factors change the relation between a trauma exposure and distress, right? So we know that if bad things happen to us, that can lead to some different type of forms of distress. But do the same people who, or does everybody who experiences the same thing experience the same amount of stress? No. What types of things change the nature of that relationship? What type of question are we asking here with this first bullet point? Anybody know? What do you think, Katie? Yeah, this is a moderation question, right? Is X related to Y in the same way across all versions of all universes, across all situations, all the time, for always and forever? Probably not, right? The nature of this relation probably changes based on different factors, and those factors that start to change the nature of that relation, these are moderators, right? Now all of a sudden, right, I'm very start to ask interesting questions about what are the boundaries, under what conditions is X related to Y, and what are the things that might sort of change that? That explodes into a whole area of research that you can go through and look at, right? We can also say what factors account for the relation between trauma exposure and prolonged distress, right? Think about mechanisms of action. What type of question we ask here? We think so. Mediation, right? X is related to Y. Why? Is X directly causing Y? Probably not. Maybe, I don't know. Or are there things that account for this relation? If I take that away, do I still see that these two things are related, or if I account for them, right? Start to ask some interesting questions about mechanistic types of things, okay? And here, what are the last one? What are the unique contributions of various risk factors to the occurrence of PTSD? Okay. Like, what things result in the development of PTSD? Is it probably one thing? Probably two things? Probably lots and lots and lots of things, right? What factors relate to sort of eating pathology or substance use, or sort of what are the things that sort of impact functioning in autistic individuals, right? Like, I don't know, it's lots of stuff. There's probably nothing I can identify in psychological science where it's just one variable produces one thing and that's the end of it, right? Here we're talking about multivariate regression, where we're saying, here are a number of different predictors. What are the relative weights of these in terms of contributions to explaining this thing that we're trying to explain, right? So again, we start being able to expand beyond sort of our simple univariate stuff. Yeah. Questions about this? Who's excited? I'm excited. I'm just get excited talking about it. Fun stuff. Okay. All right. So lots of different models. How do we keep them organized? Okay. Again, who starts to get nervous when you think about, like, okay, here's my thesis. How do I analyze this? Does that cause anxiety? Yeah. Right. This actually becomes a pretty easy thing to figure out. Once you know what your IVs are, once you know what your DVs are, things kind of fall, and the level of measurement of both of those things start to fall into place pretty quickly. Okay. At a conceptual level, what we can think about is our general linear model sort of being kind of the foundation for everything that we're going to do in this first year of stats. Okay. This is our common denominator for our univariate models, for our multivariate models. This is our internal combustion engine of statistics. Okay. It can be very simple. It can be very complex. This GLM is kind of the foundation of it, right? So this is the reason. So your Ferrari and your weed whacker are kind of similar, working on the same basic concept. Your Ferrari and your weed whacker are very different machines, but at the basis, right? If they're running on a gas engine, it's kind of still working on the same principles. Okay, this is your GLM. Okay, and if you don't need to be a math major or a statistics major or a quant person to have a basic conceptual understanding of sort of what is this doing, how do I use this to select models, and sort of how do I use this to build on sort of more and more complex techniques, right? If you have a strong foundation in regression, which you will after you finish today, SEM is no big deal. Okay, the ways we estimate things are a little bit different, but sort of the concepts carry over, right? This is going to be the foundation for any type of analysis you want to go through and jump into, right? EMA, super complicated, right? But It's just basically sort of growth, sort of expressions of GLM with more complex sort of longitudinal data. Okay, so some basic assumptions of our GLM. One, linearity. Okay, this starts to become really, really important. Within the GLM, general linear model, we're assuming that pairs of variables hold linear relationships. Okay. Basically, what we're saying is any two variables in my model should be reasonably represented by a straight line, or at least can't be better accounted for by some other type of trajectory. Okay. If I fail this violation of linearity, what's going to happen is it's going to attenuate my estimates, or I'm going to miss different things. Okay. So what we're concerned about here is nonlinearities in our data. Okay. Here, and again, this is all just stuff that we pulled off of Google. Here we have in heterosexual couples, husband's age and wife's age here. What are we seeing in these data, Jayla?
A linear relationship where
Yeah.
like as one that increases, the other also increases.
What is the strength of that association?
I think the strength is like how close the dots are to each other.
So is this indicating a very strong or a very weak association?
I would say strong.
Very, very strong, right? If we're looking at this, and who knows what the sampling is of this, it's very, very uniform. It's very, very consistent, right? It looks like as husband's age increases, spouse's age increase, like this is a very, very strong association, far stronger than probably anything that you'll ever see in data that you collect. Okay. What about this, Catherine? What are we seeing here?
Not really.
Maybe.
Not a super strong one.
Okay. What are you saying? So you're saying maybe a not a linear relation. What are you seeing here that suggests maybe a non-linearity?
There's just a lot of scatter, I guess. They're not all in a straight line. It was maybe a general direction, but not super tight.
Yeah. Kevin, could you fit a straight line to this? Yeah. So we could fit a straight line to this. And does a straight line do a reasonable job of accounting for this sort of collection of data? It might, right? Certainly not as tight as the other one, certainly not as strong as a relation. And if I'm looking at this, I see what you're saying, that there may be, maybe, I don't know, maybe a non-linearity or there, maybe a curvilinear something there, right? And if I'm looking at that, that might be something that you could explore, right? Two things to remember though. One, is there a reason, sort of given the phenomenon of interest, that I would expect a non-linearity there? Is there something about, now, do you know anything about cars? All right. I'm limited on my own, right? So the relation between horsepower and drive ratio, right? If you were in this area where you were a mechanic or sort of a mechanical engineer or something like that, and there was a reason to believe that maybe as horsepower increases, drive ratio might not reduce at a constant level, maybe I might think about like, does a nonlinear relation sort of make some sense here? The other thing too to be careful of, Jack, are we seeing a lot of dots? Is this a large sample size here? Really? Not really, right? And if we don't have a ton of observations, we are trained to see patterns, even if patterns aren't there. Always want to be careful that I'm not picking out something that might not, if I were to replicate this in a completely different sample, would I see the same type of thing? Or is this something that just happens to be a unique characteristic of these data? Okay. So what we can do in situations like this is we might go through and we might maybe fit a nonlinear curve to this, but then the question starts to become, what's the level of improvement that I can get with this, right? So if I were to run a straight line, and that straight line accounts for, say, like I get an R squared there, it accounts for 20% of the variability in my outcome. And then I run a curvilinear one and it accounts for 21%. What I got to think about is like, is that 1% enough for me to add that complexity into the model? Now, if I can say, theoretically, conceptually, there's a reason why I think this makes sense, where this might not be an exact straight line, where it might curve down, then maybe I do. But what I also want to do is not make sure that I'm overfitting data based on this individual sample. If I were to replicate this, would I see the same type of pattern again? Right? So these are the types of things that start to become important when you're going through screening, thinking about your data, not just seeing what you're seeing on the screen, but also thinking conceptually about what the constructs are that you're working with. Okay. These are all great points. People have questions about this. Okay. All right. What about this? William, what are you seeing here?
Lot of samples, generally positive relationship,
Okay.
but it's almost kind of like a half of a parabola.
Okay, almost like half a parabola. So again, similarly, you're seeing some curvilinearity here. Can you explain that? So we're looking at education and income. Is there a reason that you might expect a curvilinear relation between education and income?
Yeah, what are the number intervals on the bottom?
Oh, this is, sorry, 6, 8, 10, 12, 14, 16.
Yeah, I think typically, especially kind of the way the US society is structured, the more education you have, the more economic opportunity you have. So those who have lower years in the education system typically don't have access or don't have the training necessary for the higher paying jobs.
Right. And then once we start to get into sort of the higher level, sort of like where you all are at, right? Like you continue on and on and on to years of education, right? Would I expect that to sort of increase proportionally to? Probably not. We're kind of going to hit a wall maybe. And now all of a sudden we start to sort of increase, but the jumps that we're getting start to become higher and higher once I have PhDs, really advanced degrees and stuff like that, right? The gain that I get in going from 8th grade to 12th grade may not be the same gain that I get going from my bachelor's to a PhD, right? If we're calling those both 4 years, right? Right. There's a bigger gain there, right? And so here, right, I might say it looks like I may have a curvilinear relation between here that might actually map on phenomenologically to the process or the relation that I'm actually sort of interested in, right? And so here, if I were to go through and fit a curvilinear function, I have some conceptual basis for making a defense for that, right? Certainly, it could be just what we're seeing in these data, but I also have a reason to believe that that might be a valid sort of form of that association, right? And so, yeah, I'm on a little bit sounder footing here. Okay, Catherine, can I fit a straight line to this? Yeah, right. I could fit a straight line to this, and it would probably look something like this, right, to minimize my residuals. But I also that might not be a great fit to the data. Like I'm missing some stuff. And as I go through and I get that, map that quadratic on, what I might see is my straight line counts for maybe like 15% of the total variability. But if I map on a quadratic, now all of a sudden I'm getting like 30. I just doubled the proportion of variability in my data that I'm accounting for. That's something I should probably be thinking of being aware of, right? So again, this is you need to be thinking about visually what you're seeing, right? But then also conceptually, what am I looking at? Is there a reason to believe that I may have nonlinearities sort of going on in this data? Just making some sense to folks. Jack, what about this? Do I have linearity here? No linearity. What function fits this better than a line? Right? Does a line fit this real well? Probably not, but does anything fit this real well? No, because we just got a random scattering, right? We just got a full cloud. So here, right? And again, this starts to get into sort of the key issue here. Am I seeing a linear relation in these data? No. But is there a different function that like does capture this? No. This here, we can sort of identify this as completely random data, right? And our best fitting line is just a flat line going across, and that's the end of it, right? So would we say that we have nonlinearity here? No. Are the data linear? Technically, no, but they're not really anything. There's not something else that's better that I'm missing in this, right? So again, just a different version of this here. Okay. So again, what we're doing, we're going to go through and we're going to do a lot of screening of, we're going to look at a lot of scatter plots. We're going to look at like how our data are looking. So we're going to be attuned to potential nonlinearities, but we're also going to sort of make sure that we're not seeing ghosts, right? And saying like, oh, this is what's really going on, when it just might be a function of small samples or idiosyncrasies of an individual, of a given sample. All right, so linearity is a big thing. Other thing we need to be thinking about is additivity, okay? Idea behind additivity is that as I add predictors to my model, the idea is that so my first predictor is accounting for this piece, and my second predictor is accounting for another piece, and my third piece predictor is accounting for another piece. That each predictor that I'm adding to these models, if I have a good, efficient model, they should, each predictor I put in should be contributing something new and unique to accounting for that, whatever my outcome is, okay? So if I have, here's total variability of my outcome, okay? So this is all of it, right? What I am hoping is that I've got my first variable, variable one, is accounting for sort of this proportion of the variability in my outcome, okay? And then I add my second variable, and it's accounting for that piece, right? This one's adding new stuff. It's accounting for stuff that this one didn't get. And so I've added this other one. It's capturing sort of a big piece of the stuff that we didn't already cover, right? And then I add my third variable up here. It's adding some new stuff, right? Here we've got a beautifully efficient additive model where each variable that I'm including is picking up and accounting for different portions of variability in my targeted construct. This is a very good model, okay? What if instead I have, here's my outcome, right? My first variable captures this, okay? And then my second variable captures this. My third one captures this. Is that a good model? No, right? I've just basically included three measures of the same thing as all different predictors and pretend they're different. If I were to run this regression, what's the problem I have with this regression model? What do we call this? We know. All my predictors are highly correlated to another. Multicollinearity. Yeah, I've got a collinearity issue, right? Now, from a construct perspective, Jack, this is basically saying, oh, I've got a measure of this and a measure of this and a measure of this. But if they're all correlated 0.8 with one another, you just measured the same thing 3 different times and gave it a different name. It doesn't mean that it's a different thing. You're basically capturing the same variability across all 3 of these. And you're going to start to have problems with your model. You get big standard errors, you get unstable standard errors, things will start jumping around weird, right? So this is a problem. But motion clinical land, this is what we do a lot of time. I'm going to control for depression, and I'm going to control for self-esteem, and I'm going to control for negative affectivity, and I'm going to control for something, a hopelessness. Like this general misery, it's all the same thing, right? Like you don't need to account for it 7 different times, right? And that's actually doing a disservice to you, right? What we want to be thinking about, like, okay, we've got general misery, like what's left over? What are we not accounting for? Those are the variables that we want to be including in that model, right? And this gets at this additivity assumption. People seeing kind of with this, we're going to do a whole lot of Venn diagrams this semester. It's going to be awesome. People seeing kind of the concept with this. Okay, so if we're going through and taking a look and thinking about this, let's say that I am an economist. I'm wanting to look at grocer satisfaction. You all are residents of Laramie, Wyoming, how satisfied are you with, where would you say your consumer satisfaction is in terms of? Like, William's not got like full thumbs down, but like we're getting like close to full thumbs down, right? If I was interested in this, right, what I might do is I might say, okay, what are the things that I think start to become important in predicting satisfaction with my options, right? So maybe selection. Can I go there? Are there things that I can buy, right? Do I have options? Okay. What are my prices, right? I can have lots of prices. This is your whole problem, right? Like all sorts of options. I just sort of like don't know if I want to drop 20 bucks on a loaf of bread, right? Like that's cool to have options. I just can't afford it, right? And so I'm starting to become sort of dissatisfied with this location. Right? This is nice. Like, oh, I have a grocery store. So for those of you that miss about living in urban areas, like we got a corner store. I can just go around so to get the things I need. It's nice versus I have to hop in the car, drive across town to go through and get things, right? So dealing with traffic and things along those lines. Is location nice? Yeah, it's a great store, but it's way the hell I gotta go. Yes, grocery stores in Fort Collins are nice. I just takes me a while to get there, right? So I'm not super satisfied with that. Store layout, can I find things, right? Customer service, are people nice to me? Are they kind of shitty? And so I can go get the things I want. It's just you have to get ready to be for people to be rude to me. That's not super fun, right? So each one of these things are all kind of different components of, and if I'm thinking about grocery satisfaction here, these are all starting to sort of pick at different components of satisfaction. Okay. I would say that this is a good model. Okay? Like that one. All right. What if I'm so different question? I'm interested in personal wealth. Like what makes people wealthy, right? This is the thing that I want to know how I get rich. How do I account? How do we account for wealth, right? And so we start thinking about the things that maybe start to contribute to personal wealth, right? So I say, okay, your level of education is important, and also your family level of education, and then family wealth starts to become important. And then maybe where you live in the United States, and maybe whether or not you have training opportunities, right? These are all things that I'm arguing are related to the generation of personal wealth. What's my concern with this as a statistical model? Charlie.
I think if you have two parents who are highly educated, you are more likely to be highly educated yourself, or more likely to have more opportunities to be highly educated. So those two just kind of already overlap. And then your family wealth, if your parents are highly educated, they have more opportunities to build up their own personal wealth. And then more educational opportunities are in major cities. So geographic location also kind of, so it all just accounts for each other.
Right. Basically, I'm identifying sort of probably privilege, right? So that's contributing to stuff, right? And so maybe I'm not, these all look like very different things, but functionally they're not. They're all just different aspects of sort of this one thing that we know within our system is one of those things that drives generational wealth opportunity and things along those lines, right? These things could start to become very, very, very tied together and are all basically getting at the same thing, right? So what I've got is a model that looks something more like this, as opposed to something here where I'm getting different aspects and components and things along those lines. Okay. So this one, sort of in terms of additivity, basically I just keep adding as predictors different versions of the same thing over and over again. And so I'm not sort of really getting at sort of the total stuff there. You'll see sort of understanding this idea of additivity and sort of precursor to collinearity, things along those lines. This starts to become really, really important in setting up efficient regression models that maximize the power. If we don't do enough psychological advance to think about this, should, because it causes us problems, because then we sort of end up with models that are underpowered when they don't necessarily. All right. So what does our generalized linear model look like? Okay. If we were to put it out in math stuff, it would be sort of more than what we want to do. Like we're actually not like this isn't like a big math focused class, although it might not seem that way. Like if you get into actually proving the central limit theory and stuff like that, we'll leave that to the statisticians. Okay. if we want to go sort of a very, very simple example of this, we can just go and just fall back on a basic regression, okay? So let's say that I'm interested in looking at the relation of depression to post-trauma symptoms in community survivors with PTSD. This here is a very, very basic version of my generalized linear model. What do we have right here? We call it. What's that?
Slope.
Yeah, okay, so yep, so my B is my slope to the whole thing. This is just a regression equation, right? So what I have here, y hat, this is my predicted outcome. This is my real outcome. This is just what my model predicts, okay? A is your intercept, okay? B is your slope and X is your variable here, okay? So if we go down through and we actually run this in these data, we're saying my expected value of Y or my predicted value of Y is equal to within my model. Really, remember that my model isn't perfect. It's just sort of my best guess at a best fitting line for this to account for this data. 24.8 plus 1x is giving me my linear model here. Okay. And if I go through and I plot this out, this is what my data look like. Okay. Then what am I seeing in terms of these data? Just kind of looking at what the scatter plot is doing.
Fairly linear and from my judgment, not too close together, but definitely not extremely scattered all around. There's definitely something, I would say, not random about it.
Yep. We're seeing kind of this band of data sort of coming up, and this is a pretty tight correlation, right? This is kind of like in real psychological data. This is the type of data you're going to see. Now, there are going to be some things like here we got a point that doesn't really sort of fit with stuff, and here's a point that doesn't sort of really fit all that well. But generally, if I go through and I plot a regression line through this, this is what I'm going to get. Okay, this is the line that's going to minimize the differences of all these. Is it perfect? Does it capture everything? Not even close, right? But this is the best linear function that you can draw through this to minimize your residuals, at least with an OLS model here. Okay, and so if I'm looking at this model, Jack, based on my regression function here, what is my expected PTSD score when my depression is equal to 0?
4.8.
How did you know that?
Well, X would be the 0. And so plugging 0 into that X, it's the slope figure is just 0.
If I put in 0, my depression score, and you multiply anything by 0, that goes away. I'm just left with 24.8. So, right? So in this model, if someone has a score on the BDI of 0, my best guess is that their PTSD score is going to be about 25. Okay. People see where we got that? Okay. Jack, what is the expected change in PTSD given a unit change in depression?
It'll be like 25.8. Like, I'm not
Okay,
really
yes,
sure.
that would be what your output is, yeah. For every unit increase in in depression score, what's the corresponding expected change in PTSD? Well, you got it. 1, right? This is my slope, right? For every unit increase in PTSD, I'm expecting a corresponding 1 unit change in my, or for every 1 unit increase or decrease or change in my depression score, I'm expecting a 1 unit corresponding 1 unit change in my PTSD score, right? This is my intercept. This is the value or my expected value when my predictor is equal to 0. Starts to become a concept that's incredibly important when we get into regression. And this is my slope. What's the change per unit increase or decrease in my predictor? Okay. And this is all just basic algebra. We're going to be doing a lot of basic algebra this semester, right? It's stuff that you haven't broke out since like 7th grade. You're going to be rusty on it, but that's fine. It'll come back. You get it under control, right? But again, what I want you to be thinking of is conceptually what's going on. And what we're going to do is we start to get into our regression models. What 0 means starts to become critically important for interpretations, for sort of manipulating our regression models and things along those lines, that 0 point starts to become really important. Okay. And what we can do is we can bend our scaling to our will to sort of make that sort of do the types of things that we want it to do. So if we're thinking about our bivariate generalized linear model, we can sort of house this under 3 different forms of bivariate analysis. Again, remember that if you're wanting to figure out what analyses do I run for my thesis, first thing to do, what are my IVs, what are my DVs? What are my X's, what are my Y's? And then what are the level of measurement for both of those? If you do that, you will very quickly boil it down to 1 or 2 different options. Okay. If my X variable is continuous, my Y variable is continuous, I'm just looking at Pearson correlation. If I've got an X that's dichotomous, okay, and my outcome is continuous, I can run a point by zero correlation, or I can just run a t-test, right? Group 1, group 2 on a continuous outcome, right? These are mathematically equivalent. These are no different than one another. They're just different iterations of the same thing, right? It just really depends on, do I want to talk about this as the relation between experimental group and outcome, or do I want to couch this as mean differences between my experimental groups on my continuous outcome? Mathematically, conceptually, it makes no difference. It's about how I want to talk about this, right? I had a paper one time, and a co-author who I did not know, trying to go through, we're doing just like basic sort of like demographic stuff, like sort of looking at like inclusion, exclusion, stuff like that. And I just reported everything as correlations. As I said, there was no association between sort of inclusion, exclusion, and these outcomes. They're like, no, you can't do that. You got to run t-tests on those. I'm like, nope, you for sure don't. Because I don't want to have to go through. It's easier for me to just say, hey, there's no association between inclusion and sort of these different outcomes. That's an easier thing for me to talk about than marching through each and everything and saying there were no differences across inclusion and exclusion groups about just like, I'll just give you a goddamn correlation that just covers it, right? Now, did I have to do it that way? No, I could have went through, but it was just easier for me to present it that way. So I went through and sort of decided to do this. Now, if I were to have, let's say, Jayla, you have a control group and an experimental group that you've set up and then you run and measure on a continuous outcome, should you report those point by zero correlations? I wouldn't, just because that's not how people are going to probably expect you to talk about that. If you say, I have these 2 groups measuring on some outcome, just report it as a t-test, right? But mathematically, your p-value is going to be identical across those 2 because of math. Like that's just the way it works, right? The only consideration is here is how do I want to present it? Now, if I have a X that's dichotomous and a Y that's dichotomous, same thing. I can present this as a p coefficient, which is basically just the same thing as a Pearson correlation. It's just with 2 dichotomous variables, 0, 1, 0, 1, or I can present it as chi-square. Again, mathematically identical, no difference, right? It just depends on, a lot of this will depend on within your literature, what do people expect to see, okay? Same thing as we were talking about last semester, right? If I've got an ANOVA with 1 degree of freedom in the numerator, right? What am I up? So I can talk about sort of a one-way ANOVA, or what is that equivalent to? Does anybody remember? It's kind of reaching way back in the. You got it, Katie?
Say it one more time.
What is
Can you
it?
say it one more time?
So if I've got an F with 1 degree of freedom in the numerator, what am I talking about? Just a t-test, right? And sometimes, I mean, I do this stuff and sometimes it throws me off, right? If I got someone's reporting 2 groups and then they're reporting their statistics as an F, it throws me off a minute because I was expecting a T, but it doesn't matter. You can report it as an F, that's fine. If you take the square root of that F test, it gives you a T. It's completely interchangeable, right? Me personally, I don't like to sort of like violate this sort of expectations, because then people who don't know the difference will get angry, and then I got to explain to them when it's probably just on me. I should have just done it the way people were expected to do it in the first place, unless I've got a good reason not to. Same thing here, right? People are expecting this t-test, give them the t-test unless you got a good reason not to, right? People are expecting a chi-square, just chi-square, that's fine. Just report this as your effect size, right? in both of these situations, the fee and the point by serial are actually more meaningful statistics in and of themselves. They carry more information. These are indices of effect, but I'll just report those two then along with the T unit if it makes people happy. I'm not trying to like create problems for myself, right? So again, just knowing how to go back and forth between these starts to give you flexibility to be able to be sort of more successful with less headache in sort of talking through with reviewers. Okay. Questions about this? Okay, cool. So again, analyses, functional equivalent. Mathematically, they're the same. P-value for both of these are going to be identical. P-values for these are going to be both of these identical. It's just when we're presenting things as correlations or sort of correlation methods, we tend to talk about these as associations versus group level differences. You just have to think about like what's the most efficient way to go through and present this to my audience. All right. Thinking about sort of benefits though, conceptualizing GLM effects as relations. Okay. We can take this bivariate form and extend it to sort of more increasingly complex analysis. That's sort of the good thing and the bad thing about everything that we do across this first year is it all builds on one another. And this is one of the things I love about statistics and analysis is once you get this level, you just build the next level and the next level. It's all additive. Problem is, if you don't understand a thing down here at the basics, like it's not going away, it's going to continue. It's like a bad penny. It's just going to keep coming up again and again and again and again, right? Same thing here. So if you've got a good handle on t-tests, mean-based analyses, things like that, sort of leveling up into continuous stuff is just an extension of this, right? It's the same thing. It's just kind of in a slightly different form. And we can expand this out to include multiple predictors of my outcome. Okay. When I have multiple predictors, it starts to become more difficult to start talking about things as mean differences, right? Whereas if I'm identifying this as the association of group membership with my outcome, it makes it easier to start adding other things in as opposed to me being stuck talking about group level differences. Okay. So again, if I'm interested in looking at the unique association of depression, trait anxiety, and social support, PTSD, and survivors of motor vehicle accidents, I can go through and do this, right? I can say, okay, I'm using wanting to predict outcome on my PTSD variable. And what I'm doing here is I'm including and estimating the weighted quality of my predictors of my measure of depression, my measure of anxiety, and my measure of social support here. All three of those can go into my model. And what my model is giving me is the unique effect of each of these after we're controlling for how these things relate to one another. Okay. And we'll end up doing a lot of Venn diagrams to kind of illustrate what this looks like in function. Okay. Thing to remember, in our multivariate analyses, these coefficients, I don't know if these are standardized or not. These might be standardized coefficients, probably they are. These are representing partial effects. Okay. Thinking back to last semester, when were we talking about partial effects? Yeah.
Factorial ANOVA?
Yeah, factorial ANOVA. And what were the partial effects that what specific partial statistics were we looking at there?
Eta squared partial and omega squared partial.
Yep, partial omega squared, partial eta squared, right? We're saying this is the proportion of residual variability in my outcome that this factor is accounting for, or we pull out other things in the model, right? This is exactly any of our regression coefficients. This is exactly what it's doing. So after we pull out variability that we can contribute to anxiety and social support and the combination of these, of what's left over, this is what this is capturing. Okay. So once I go through and I pull out, and this is the problem here with this nest of predictors here, I got variable 1, and then kind of variable 2, it is kind of accounting for some stuff that's left over. But then when I throw in variable 3, that sort of starts to take away some of that type of stuff here. Again, and this is the difference between our regression models with multiple predictors and our correlation. Correlation is just our bivariate 1-to-1, right? Here, what we're doing is we're parceling out other things, and we can start to be strategic in how we do this in order for our models to ask the questions or answer the questions that are of most interest to us. So again, wanting to be very thoughtful and deliberate and intentional about how we're building these models, and what they mean. And we don't do a good job about with this in psychological science. Again, experimental folks, you do a little bit better with this. Us clinical folks don't, right? It's just like, here's some variables and we're just gonna throw them all in the hopper and see what happens. You can do that. I've done that before. Sometimes still do. It just, you gotta be careful in terms of sort of what that means and how you go through and interpret things. Questions about this? So, if we're talking about this as our simple multivariate GLM, okay? And our X's, we've got a number of X's and one outcome still, okay? If I've got a continuous set of predictors and a continuous outcome, I'm talking about a regression model. Okay. If I've got some sort of discrete predictors and continuous outcomes, I'm working with ANOVA. Okay. This is actually, so last semester we did work with a simple multivariate model, our factorial ANOVAs. That's what this is, right? If I have a mixture of continuous and discrete predictors and a continuous outcome, this is generally something we would analyze in an ANCOVA, although we use this wrong all the time. We're going to spend some time talking about one of my favorite papers ever talks about like sort of, you don't just ANCOVA stuff because that's not probably doing what people want to do with it. If I have continuous predictors and a categorical outcome, we can run this with a discriminant function analysis. You don't see these too much anymore. It's basically like a reverse factor analysis. There's some squishiness in interpretation, so you don't see a lot of DFAs too much anymore. But if I've got a mixture of continuous, discrete predictors and a categorical outcome, this is where I'm working with logistic regression. These are fantastic models that we don't use enough, but they're very, very flexible. We should make more use of these in psychological science. If I've got a mixture of continuous categorical, my outcome is some time to event. We're talking about things like survival analysis. If I've got time and a mixture of continuous categorical variables, a continuous outcome, talking about time series stuff. I took a whole like summer workshop on time series at the University of Michigan when I was a grad student. Never have found out that statistical model and the types of stuff that I do, right? But it was it was actually my first introduction to Stata, which is I didn't know. So it's sort of coming back like later, the love affair that would be. I do remember sitting there. I go, oh hey, this is way slicker than SAS. But some different analyses there. Okay. All right. So questions about our simple multivariate GLM. All right, cool. All right. So to this point, if we're thinking about our simple multivariate GLM, this is good. We've expanded the number of predictors that we can include in our model, but what we could do is we could level a lot of the same criticisms of our bivariate analysis against our simple multivariate model. You can say, well, they're cumbersome and inefficient, right? Limited in the types of relationships that can be assessed. What if I want to have multiple related outcome variables? I just got a lot of sort of my outcome and sort of like William with your analysis when you're working with like a MANOVA stuff, like what might be the collection of DVs that you might be interested in like a MANOVA model that you all are working with? I don't know if you've been in sort of on any of those papers or anything, but just kind of give me an example. So maybe like cravings and sort of like number of use and sort of problems with say alcohol use or something. So you've got kind of this constellation of things that are all kind of their own thing, maybe a little bit, but like are kind of all around sort of alcohol related impairment or something like that, right? Same thing, Finn. So if you've got some eating outcome variables, right? You've got maybe perception of weight, shape, sort of restriction, compensatory, but like sort of kind of this collection of stuff, right? Well, do I want to run a regression, like 7 different regressions with each one of these? Maybe not, right? Maybe it would be nice if we could go through and collect these together and sort of run some sort of model here, right? Same thing, example, what's the relation between gender and college performance? If we've got all these different sort of outcomes here that are all getting at different pieces and part of this idea of college performance, I could go through and run a multivariate model with each one of these as outcomes, or what I could do is I could run a full multivariate GLM. My full multivariate GLM, what I've got is I've got multiple predictors and multiple outcomes here, okay? Mathematically, this is what this looks like, okay? I've got outcome 1, 2, 3, so on and so forth for however many I've got. Pit against predictors 1, 2, 3, however many so I've got here, okay? What we're starting to get is a very, very complex model with this, right? And so if we're thinking about how do we go from our basic regression model to a regression model with multiple outcomes, basically what we end up needing to do conceptually mathematically with this is we often need multiple equations to go through and account for this, okay? With a standard regression, right? Jackie, you did a nice job. You say, okay, here's my regression model looking at the relation between depression and PTSD. And if I have an increase in PTSD, what is the corresponding expected result on my, or well, an increase in depression score, what's the corresponding increase in my PTSD score? Well, I just sort of plug that in the model and sort of tell you what the score is, right? With my full multivariate GLM, I can't do that, right? Because I need to have, so here's what it might do to this outcome, but maybe it does something different to a different outcome and something different to a different outcome. What I need is multiple, oftentimes multiple equations to go through and solve this, okay? This is similar, again, going back to 7th grade algebra, right? Thinking about, Cindy, can I go through and create a unique solution for x plus y equals 24, right? There's an infinite number of solutions to that, right? But if I go through and I add in another equation, so x plus y is 24, also 2x minus y is -6. Now I've got two equations, and with this, I can come up with a unique prediction or a unique solution for x and y both with this, right? Same type of thing when we had going into our full multivariate types of analyses. What we need is we need a set of equations to go through and solve this and come up with a usable solution. Okay. Now, the term for these linear combinations, these sort of, we'll talk about solutions as linear combinations, depending on what analysis you're using, the terms are different, right? We'll talk about these as characteristic roots, that's a DFA term, right? Principal components, that's an EFA term, but it's all talking about the same thing, right? What we're doing is we're using a set of predictors for best linear combination of outcomes, and what we'll often need is multiple equations to go through and solve this. In terms of versions of my fully multivariate GLM, if I've got a set of continuous predictors and a set of continuous outcomes, historically we've looked at these with something called canonical correlation. I've never actually seen a paper with this. There are problems with interpretation, but like, so if we were to do that, that's a sort of tool we could use. We don't see that a whole lot. If I have a set of discrete predictors and continuous set of continuous outcomes, now I'm talking about MANOVA stuff. Okay. If I've got a mixture of continuous and discrete predictors, continuous outcome, MANCOVA. Right now I'm running a MANOVA with covariates, right? I'm sort of doing this. Here's the one that we're going to spend some time with this semester. If I've got discrete predictors and continuous observations, talking about repeated measures ANOVA. This is incredibly powerful. There's some cool stuff that we can do with this. If my predictors are latent, right? They're not observed. I have indicators that are some version of this. And so I have a continuous predictors of sort of this latent variable. I'm getting into principal components, principal factors, things along those lines. If I have some combination of continuous, discrete, latent, X is continuous discrete latent, outcomes. Now I'm looking at SEM stuff. And this is, SEM is probably the reason why, with development of these models and sort of access, like at one point, like you could only run these if you had very specific sort of like coding types, Levon type of like programming and stuff like that. When we're thinking about the development of SEMs, Jayla Amos was really kind of a big kind of leap forward with that, and SPSS ended up sort of buying that, I think, sort of taking that over, because then that was more of a diagramming, and so then once you drew what you wanted to do, sort of the program puts in the models, right? M plus is nice, it's a nice in between, like M plus is kind of like the state of sort of SEM stuff. You still type it into a kind of a thing that you want, but the programming language is easy. It's not like kind of crank through stuff with R, Levon, and some of those types of programs, right? But this starts to become a more elegant solution for dealing with multiple collinear outcomes than sort of maybe some of our other stuff. So a nice, very, very flexible tool there. Questions about our fully multivariate GLM? Yeah, Pin.
Is it safe to say we don't have to worry too much about canonical correlation?
Yes, no. The only thing that we're going to go through and spend some time with, formally in class, is repeated measures, ANOVA, stuff like that, right? But Tabachnik and Vidal have really fantastic chapters on all of this stuff. If you were to find occasion to need to go through and look at this, that would be an excellent guide where I would look at first. I used to have PCA and factor analysis sort of included in the class, but it started to become so hard to get all that put in. I've got some like sort of video on that, but I think I'm going to go through and try and put together more. It's like me in the dark, like yelling about EFA over in arts and sciences computer lab. Sort of it does the trick, but I'm sort of going to try and put together a more efficient screencast for that. But yeah, this is what we need to work on here. All right, so where do we start? Well, we'll start with a break for right now. So let's go through take 10, come back, and we'll start in with some basic correlation stuff. Okay. All right. Questions about anything we've covered up to this point? You'll just get a general sort of idea about sort of general linear models and kind of basic concepts and things. Okay. What we're going to do is we're going to jump into some correlation stuff. And sort of thinking about correlation, this is going to be our sort of kind of a basic fundamental unit of measuring associations, and probably not going to have papers where you are limited to sort of analysis of correlation matrix, but there are certain things that we can start. I think the correlation has potential that's underutilized that I think we can sort of use for some specific questions and have effectively. And so we're going to talk about some different things we can do with some of these coefficients. To start off, we're talking about correlation or regression, right? If I've got one predictor and one outcome, I can run this as a correlation, I can run this as a regression. They're mathematically equivalent. They're not really doing anything different. But there are some important differences in terms of the underlying assumptions of these analyses that we probably need to be aware of. And if I'm looking at a correlation, I'm looking at a measure of association between a random variable X and a random variable Y. Okay. If I'm talking about a random variable, I'm talking about a variable where this is what we would typically think about as a variable. There's just some pool of participants, and I'm just randomly picking people out of there and measuring that observation. Okay. What we see with our correlation mathematically from a model-based standpoint, I'm assuming sampling error in both my X and my Y, right? So I'm going to have my measure of X, my measure of Y, and with a correlation, I'm assuming that I've got sampling error in both. With a regression, however, what we're doing, this has historically been so conceptualized as a prediction model, right? Which is more sort of causal in nature. What we have here with our regression is we're assuming a fixed variable x to predict observed values of random variable y. Okay, we'll get into this a little bit more, but the idea, random variable y, whatever my sort of participants I pulled in is whatever their variable, the value is of their outcome is whatever the value is of their outcome. Okay, but I'm assuming here that x is fixed. X means that my values of x are not random. I'm assuming that I have in my regression model observed all possible values of x that are relevant to my question, right? There's no distributional assumption associated with this. It's saying I've systematically gone through and I've got pulled 10 green marbles, 10 blue marbles, 10 red marbles, 10 yellow marbles, and 10 black marbles, and 10 white marbles. Those are all the marbles I'm interested in. I've got 10 of each of them. Now, what the outcome, what the Y value of each one of those marbles is anybody's guess. That's random. But I've systematically gone through and sampled for my fixed variable X. And I'm using this to predict my outcome. Okay. And my linear regression model, it assumes sampling the variable only in my Y outcome. Okay. And there's some implications of this. I'm assuming that I've measured my X without error, right? That my value of my predictors is perfectly reflective of whatever construct that I've gone through and am interested in. Do we ever do this actually? No, we always violate this assumption, right? So there are some additional things that we need to think about as we're working our regression model to make sure that we have confidence in our estimates. Okay, so some fundamental differences in the assumptions of our regression model. Here, if I'm looking at the relation, again, this data that we've already looked at, here's a BDI score and my CAP score, my PTSD score. My correlation here is 0.535, okay? And this is a perfectly valid sort of correlational model here. I've randomly selected people who have some value of BDI, some value of CAPS. I'm not in charge of what those are or systematically sampled for anything. I've got random X, random Y. There's a linear relation between these two. And I'm assuming that I've measured both of these things with air. This is a perfect model for a correlation here, okay? And my correlation model right now, Charlotte is 0.535. What does that suggest about the association between BDI score and PTSD score in these data?
It's like a moderately strong association
Yeah,
between them.
this is
It's a positive.
sort of a positive and strong association here, right? It's actually strong correlation here, right? So we think about 0.1, 0.3, 0.5, right? So we've got a very strong association here. Okay. Properties of my correlation coefficients, bounded by -1 and 1. Okay. I can't sort of get beyond those bounds. Now, I've asterisked this. Our standardized regression coefficients, our partial regression coefficients, those can exceed -1 and 1. They typically don't. If they do, you want to sort of make sure that there's not something weird going on in your data. But my standardized coefficients can sort of go through and exceed 1 and 1. So you need to be aware of that. Some things that people will do with those coefficients that you shouldn't do that are not appropriate. We'll talk about that. The value of our correlation tells us the magnitude of the association, right? How strong it is. And sort of depending on sort of how our data are coded, the value, whether it's positive or negative, we can sort of draw inferences about the direction of those data. Okay. What starts to become tricky is if I've got a measure of happiness, increasing scores might mean greater happiness, increasing scores might mean decreasing happiness. It all depends on how I scale it. So you just have to be really cognizant of correlation, sort of making sure that you're specific on the direction, because the sign won't necessarily tell you unless things are coded in a way that's kind of intuitive. So just always be careful with this. When you're working on your problem sets or doing anything, don't just tell me there's an association between X and Y, because that doesn't tell me anything. Tell me with increasing X, we're seeing decreasing this, or increasing this, increasing that. Same thing as with our t-test. Don't just tell me there's a difference. That doesn't tell me anything. Tell me what direction that's going. Okay. All right. Who is super confident in correlations? Awesome. You know, you put your hand down. What you do, you got an assignment. We got here, if you look at the bottom of this, so we got sort of guess the correlation here. All right. It's a fun game. It is better than Sega Genesis, right? You're gonna get to go through and guess correlations. What I do, here's the thing, it's sort of contest. Once you go through, guess the correlation. We're gonna keep a high score posting. So they're like, you gotta give me a screenshot. I'm not just gonna take your word for it, for your high score on guess the correlation. At the end of the semester, we'll have a prize, a special prize for whoever wins, has the highest score for guess the correlation. This is a big deal. Like you'll for sure want to, what?
So where are we gonna see these scores?
What's up?
How are we gonna see the scores?
You're gonna sort of do it, and so then you're gonna give me a screenshot of your high score here.
Just the high score, are there limits
Yes,
on
exactly.
the number of attempts?
No, it's like sort of just
Sold
work
it.
on it.
Come
Right, Jayla, are you playing guess the
So
correlation?
exact, 0.59.
Nice, great. Look at that. He already wins. I guess no one else has to try anymore. All right. This is the thing, right? This is actually a fun game.
I'm so sorry. I'm so sorry. I thought I turned.
That's right. If it was anything other than guess the correlation, I'd be pissed. I don't understand. No, this is fun. Like, and it starts to become surprisingly difficult to sort of like figure out and sort of guess those. But it also does, I think, sort of a nice job of like as you're going through and looking at scatter plots, thinking about sort of magnitude correlation, things like that. Yeah. So put that on, right? Like send me high scores. We'll sort of keep a leaderboard up there for prizes at the end of the semester. So all right. Want to go through, do a quick review of some basic concepts involving variability. Okay, we spent a lot of time last semester talking about variability. In general, when we're thinking about variability, we're just talking about the extent to which scores are spread out or clustered together. Okay, if all the scores are the same, there's no variability. You don't have variability, you have constant, right? If wildly or different scores, got large variability, things are spread out all over the place, right? Thinking about conceptually, some different ways we can start to think about conceptually about variability in terms of our estimates and things along those lines, right? We can think about variability as describing a distribution in terms of distance, right? If you give me a measure of variability, that's telling me how much distance to expect between two randomly selected scores or some randomly selected score from the mean, right? And within a means-based analysis, someone tell me, what did we kind of conceptualize variability as? Experimental condition is the only thing that determines my outcome. Everybody in a specific experimental condition should what? Have the exact same score, right? If they don't, what do we call that, Catherine? Error, right? And so we can think about in a means-based analysis, we think about variability as a measurement of error, right? If my model was perfect, I should see no variability around my mean, but the fact that I do suggest that there's some sort of source of error in here. So there's some variability that I'm not accounting for. Now that could be random variability, it could be systematic variability. I don't know. That's a question I need to ask myself, right? But if I'm thinking about in general, variability telling me the distance between any two randomly selected scores or the mean in any score, telling me how precise my estimate of my mean is, right? We can also think about how well some individual score represents the full distribution. Okay, if I'm looking at age of graduate students, and I take the mean of age of graduate students, is that a pretty good measure of? Is that mean going to be a pretty good representation of the distribution of age in graduate students? Age in graduate students, so we'll say doctoral students in PhD programs. Probably. I mean, who's the youngest right here? Like who's Jack? How old are you?
22.
22. Who's the oldest? 25. About 3 years. It's a pretty tight, so there's not much going on here, right? So if we were to go through, there's not a ton of variability. Now, if I were to say variability of faculty at the university, is the average age of a faculty member at the university going to be a good representation of sort of the entire distribution? Not so much. You're gonna have people who are very young to very sort of ancient, sort of creeping closer towards ancient than young, right? But so we're thinking about how well a score represents sort of my distribution as a whole, right? And so this then gets us into error, right? If I say, if you tell me the average age of a graduate student at the University of Wyoming is 23, or sort of in doctoral programs in psychology is 23, and Katie, you pop up and you make, how old am I? You say 23. I'm gonna guess I'm pretty close with that, right? If you say the average age of a faculty member at the University of Wyoming is 45, and some random faculty member pops up and says, how old am I? What am I gonna guess?
You're on the side of younger.
Be systematically wrong, right? If the mean is the mean is the most representative, but am I really sort of confident that I'm gonna be close with that? I'm probably gonna be off by a bit, right? It's still statistically my best guess. But, and we're assuming that I can't see this person right now, obviously, if you sort of see me and, I don't know, how old do you think I am?
Let's all pick a
45.
number on a count of 5.
But I am 45 right now, yes, so you're right, I guess I did not realize I.
Oh, I said 25.
What did you say?
25.
25. Yeah, I was I was 25 in my second year of graduate school. I sort of took my time. I was sort of sort of not in a rush to sort of get through anything. But so yeah, sort of thinking about in terms of variability, one, variability of faculty at the university is going to be much more variable than age of PhD doctoral students in clinical psychology, is you know, much less, right? So just in terms of thinking about variability as a metric of representativeness of sort of the mean or the given score of everything. Okay. All right. Thinking about variance, okay. Here we're talking about variability as just a general concept. Variance here we're talking about a specific statistic, specifically the second population moment. Okay. Again, thinking about variance is going to be the average square distance from the mean. Okay. And we can think about, if we take the variance, take the square root of that, we end up with our standard deviation. Thinking about standard deviation is loosely interpreted as the average distance mean score, randomly selected score from the mean. Okay, we say loosely because it's not technically the average. It's take sort of that sort of sum and sort of divided by n-1, so it's not technically the average, but for all intents and purposes, it's sort of pretty close to the average, right? So again, sort of recognizing sort of mean or variance and standard deviation as specific sort of forms of or metrics of variability. Okay. We've seen Bill and Ted's excellent. Awesome. All right. Finn wins. Everybody else knows. So like here we've got yeah, it's a classic. I was thinking about like, so maybe I need to update sort of images on my slides. But I actually don't change those too. So
Good movie.
Excellent Adventure. It's a good movie, right? It's a fun, it's like a history lesson here. Right? All right. Quick reminder on variance here. Okay. Remember what we're going to do with variances. We're going to go through and we're going to have our X values here. Okay. And what we're going to do is we're going to subtract the mean of the sample from each one of these. It's going to get us a set of deviation scores. Okay. Anytime someone's talking about deviation scores in statistics, it probably just means sort of the vector of scores representing the difference between the observed and the mean. Okay. Then we're going to go through and we're going to square those deviation scores. Okay. Why are we squaring these deviation scores, Charlotte? Makes it hard to interpret because we just squared everything, right? Like what benefit does squaring these deviation scores have for us?
It makes them all positive.
Makes them all positive. What happens if I just sum up these deviation scores? What am I going to get? 0, right? So I can't just sum up those deviation scores. I gotta do something with it, right? And so for here, for the calculation of variance, what I'm gonna do is I'm gonna square all these and then I'm gonna sum those up, okay? And this is gonna give me my sum of squares. This is literally the sum of my squared deviations. And this is just a very raw metric of variability. It's critical for the calculation of statistics, but it doesn't do much for us interpretively, right? I can't look at a sum of squares and tell you if that's a big sum of squares or not a big sum of squares. It all depends on the metric, right? There's not a lot of interpretability there, but it's just a raw metric of variability in our data. What I'm then going to do is take that sum of squares and I'm going to divide it by the number of observations in my set minus 1. This is going to give me my variance, okay? And then I can take that variance, take the square root of that, give me my standard deviation. And now we're in something that makes a little bit more intuitive sense, thinking about this as sort of roughly the average distance of any randomly selected score from the mean of the distribution. Okay, starts to give me a better sense of distance. Okay, but all of these are just different versions of the same thing. We're just sort of modifying the expression. It's all coming back to people. All right, computational formula there. All right, so the new thing we're going to add into this is covariance. Okay, covariance is a metric of the degree to which two variables vary with one another. Okay, and calculation of covariance is going to be the sum of the deviations of x and y for a given set of variables over n minus 1 number of observations in my sample. So let's say again we go back to our BDI and our PTSD scores here, okay? And here's the mean of BDI, here's the mean of my CAPS scores, okay? If I have a situation like we have here, where I'm pairing large values of X with large values of Y, the sum of those products is going to be large and positive, okay? So if I have a large X, right? So the deviation of, say, this score right here from the mean is going to give me a large positive value. And the deviation of, or let's say this score right here, deviation of this score from the mean of X is going to be large and positive. Deviation of the score from the mean of Y is going to be large and positive. I'm going to have a large positive number, but multiplied by a large positive number is going to give me a large positive number. Same thing down here. If I have small x's and small combined with small y's, here I've got a small x and a small y. Deviation from the mean is going to be a large negative number. Deviation from y is going to be a large negative number. If I multiply a large negative number by a large negative number, what do I get? Large positive number. So I'm going to get a positive covariance here. Alternatively, if I have large x values paired with small y values, what's going to happen is I'm going to have, let's say I've got a large x value paired with a small y value, something down here, right? Got a large x paired with a small y. So I've got a large x deviation that's going to be large and positive. My y is going to be large and negative. A large positive and a large negative number multiplied together give me a large negative number. Same thing if I go small x's and large y's. I've got a small x. It's going to give me a large negative deviation paired with a large y. It's going to be a large positive, large negative, give me a large negative number. So you have a negative covariance telling me that I've got a sort of a negative association right here. But if I got a situation where x's are unrelated to scores on y, large x's sometimes going to be paired with large y's, large x's sometimes going to be paired with small y's. What's going to happen? Everything's going to cancel each other out. And I'm going to get some value very close to 0 with this. This is where I've got a scatter of all of this here. So just wanting you to think sort of covariance is one of those things similar to variance. Just back, oh, this is a number, it's statistics, and I don't really understand where it comes from or how it's calculated. Don't do that, right? For the types of things you're doing, you want to at least have a conceptualization of kind of what this represents, what it is, and what goes into the calculations. Questions about covariance? All right. Up here is computational formula for covariance. It's sort of an easier way. This by definition is sort of an easier way to go through and calculate. And so what we know about covariance, this is a joint function of the standard deviation of X and standard deviation of Y. Okay, now this is where we start to get into some differences with the calculation of correlations with continuous variables versus our discrete groups metrics. If covariance is a joint function of the standard deviation of X and Y, what happens if I have data that doesn't have a lot of variability in it? What happens to my correlation? It shrinks up, right? If I'm wanting strong correlations, I want sort of large ranges, right? Large variabilities. It's going to help sort of generate a strong proper estimate of my correlations. If I get restricted range, things start to become abnormally small, right? And maybe sort of give me unrealistic expectations of the magnitude of the association between two variables here. Okay. So, but we know that covariance is joint function, standard deviation is standard deviation of X and Y. Covariance in and of itself, I can't look at a covariance and tell you if that means anything good, right? It's just a number. So it's like if I were to look at some squares or variance, can't tell you much of that. But what we can do is we can take covariance and divide it by the product of the standard deviation of X and Y. And what this is going to do is it's going to standardize this. Okay. As soon as I take that covariance divided by the product of the standard deviation X and the standard deviation of Y, what this is going to do is it's going to turn this into a Pearson correlation. Okay. And now all of a sudden I have a statistic that's bounded by -1 and 1. Okay. Where the absolute value is very interpretable and very helpful in terms of gauging the magnitude of an association. Okay. So think about correlation is to covariance as standard deviation is to variance, right? We're just sort of rescaling that to be more useful in a way that's useful for us to go through and look at stuff, right? So if you see something talking about the covariance between X and Y or a covariance matrix or things like that, don't get scared or be like, oh, this is wild. They're just talking about a correlation matrix. Like a covariance matrix, if you just standardize it, just a correlation matrix, okay? It's just looking at the associations between variables. Okay, so this is our loved Pearson correlation. So the thing to recognize though is that our Pearson correlation is not an unbiased estimation of the population parameter. And this is rho. This isn't a p-value. This is just Greek rho. That's the population sort of symbol for a correlation. When I have small samples, my correlation coefficient is going to be too large. Okay, it's going to be a bias estimate of that population value. And so if I have small sample, if I'm working with a small sample, what we can do is we can sort of apply an adjustment to that Pearson correlation to help bring that sort of closer to what the population value is likely to be. And again, this is just an adjustment based on sample size. As your sample size gets larger and larger and larger and larger, the penalty that you're getting for small sample size can get smaller and smaller and smaller. If your question is when should I apply an adjustment to R, I don't know. Right? I mean, if you've got an obviously small sample, if you're looking at a correlation with a data set like 30, that would probably make sense. If you got 50, I don't know, calculate and see if there's a difference, right? So, well, if you got 100, so again, just being aware, what starts becoming more important for our purposes, recognizing that if you are going to sort of build power analysis for your thesis around a paper that's reporting a correlation with a sample size of 25, just know that that correlation is probably way bigger than it should be, and sort of recognizing that sort of the vulnerabilities of going through in a STEM, sort of using that as kind of your estimate of what's going on out there in the universe. Questions about this? Cool. Testing significance of our correlation coefficients. Okay. Null model. All right. Here, another thing to write this down somewhere. Anytime I'm asking you to give me to describe your null model, again, remember that we're talking about populations. Okay. You got to tell me that. If you don't tell me what population we're generalizing to, I'm going to tag you on it, and it just happens again and again, and then I get frustrated and you get mad because you keep losing points for something that arguably told you lots of times before, just make sure, and again, this isn't just like sort of my own, I mean, it is kind of my own peeve, but I just think in our field, like, we just do not do a good job of thinking about like who we generalize this to, who did I sample, who's my target population, right? So I just want you, anytime you approach analysis, I want somewhere in your head to be thinking about like what's the population we're trying to generalize to. Now that can make us feel bad sometimes because whether or not sort of University of Wyoming undergraduates generalize to everybody in the universe is sort of kind of a question. It depends on who we're talking about, right? But it's as responsible scientists, I want us to sort of shoulder that sort of discomfort, and sort of think carefully about what that means for our analysis. Okay, so for our correlation coefficient here, our null model is that rho is equal to 0, population association, population effect is equal to 0. X and Y are functionally linearly independent. They're not related to one another. My alternative model is that it's just some value that's not 0. Okay. Similar to sort of our means-based test, is this a useful alternative model? What do you think, Finn?
Not really, because it just, I don't know how to avoid a double negative, but it not being related doesn't inherently mean there's a meaningful relation.
Just because something isn't the estimate isn't 0 to like 14 decimal places doesn't mean that I have a meaningful association between anything, right? And as our sample starts to get stronger and stronger and stronger and stronger and stronger, if you're working with large sample data, like there's for sure that you get correlation of 0.08 that's less than p less than 0.00001. It's just basically a function of how big your sample size is, right? So just remember that that's what we're looking at. This is what our analysis is testing, is whether or not this thing is exactly 0, right? So I might have already was 0.12. Cindy, is that an important correlation? And on context, is that a significant correlation? Depends on how many people I have, right? Like if we start like sort of really like sitting with this, like the arbitrariness, or whatever that word would be, is really sort of, I don't know, it makes me uncomfortable, right? Sort of given how much sort of effort or how much weight we give to something is statistically significant. Like if I have a sample of 30 people, I'm going to call that trivial and neo 0. If I have a sample of 500 people, I'm going to say this is highly significant and sort of make a big deal about it, right? When it's the same goddamn estimate, right? Like the association doesn't change. It's just the p-value that we attach to it, right? Which isn't necessarily a bad thing. It just needs to be, we need to be careful in thinking about, and this is where, again, if I'm tagging on problem sets, saying, well, what's the practical significance, right? Now, just because this isn't big doesn't mean it's not important, right? But this is just an estimate of the magnitude of our association, right? So wanting to think about like, sort of what would this mean if these things are related large scale over a population, that could be huge, right? If this is sort of like, here's the correlation between this thing I'm trying to change in therapy and some outcome, this is maybe not doing it, right? So it really depends on sort of the context, right? But recognize that this coefficient, so the number of the zeros, so it's associated with your p-value, is just a function of how big your sample is, right? So we got to be careful about sort of falling back on significant stuff, okay? Because all we're testing is that sort of our population association is at 0 to an infinite number of decimals, which will always be, we'll always reject the null if we have a big enough sample. Okay. So just kind of keep that in mind as we're going through an interpretive search. Okay. Now, if we're going to go through and run our formal test of our null model here, remember again that our null model is just our description of the data, right? So we're just saying, does this model do a good job of accounting for the data that we're seeing? Okay. What we know about the sampling distribution of R, assuming a null model, is just going to follow a t-distribution with n-2 degrees of freedom. This makes this really nice. Okay. So if I look at the relation between X and Y, right? And I were to go through and say have a sample of 50 people. If I go through and I measure that with one sample and then another sample, and another sample of 50, and another sample of 50. And I do this for all possible size samples of size 50 that could be drawn from the population. What I'm gonna get is I'm gonna get a distribution of correlation coefficients. And that distribution is gonna follow the distribution of a T statistic with degrees of freedom at -2, 48 degrees of freedom, if 50 is my sample size. Which makes this really nice because what I can then do is I can get a p-value for my correlation by getting a t-value and then sort of getting the p-value for that t statistic. Say, so here what I'm going to do to get my t statistic, I'm going to go through and I'm going to take r times the square root of n-2 over square root of 1 minus r squared. That's going to give me a t, and then I just figure out what my t-value is, plug in the degrees of freedom in my p-value calculator. It's going to give me the test statistic for that. People see what we're doing here? This is nice. We're using T, we know T, we like T. What's nice is this Pearson correlation is following a known sampling distribution, which makes it easy to go through and assign probability values to this. Okay. Other thing though is I would argue so more relevant and interesting and useful is thinking about our Pearson correlations as a measure of effect size. Okay. Thinking about this as giving us an estimate of the magnitude of an association with a population. Okay. So going back, Charlotte, sort of looking at that relation between depression and PTSD was 0.55, but we're sort of exceeding sort of our traditional benchmarks for a large effect like this, right? So wanting you to, these are not sort of stone tablet come down from the mountaintop things, but it's just a general guideline for gauging, general metric for sort of strength of associations. Okay, so be careful with that. What we can also do is we can go through and we can sort of run a straightforward transformation between R and D, right? Now, if I have sort of a continuous measure and a continuous measure, and I'm looking at association and for an effect size between that, do I want to turn that into a D? Probably not, because I think about D as a metric of standard deviation differences between groups. If I have a continuous variable and a continuous variable, do I have any groups? No, so I don't really know how to sort of give a meaningful interpretation of D. I can do it, I just don't know what conceptual meaning I would attach to that. So I would probably just keep it with R, right? But if someone has gone through and looked at sort of the relation to an experimental group, sort of group 1 and group 2 with some continuous outcome, and they've reported an R, and you, Cindy, are like, okay, well, this is a relation between PTSD and not PTSD and fatalism, right? And you're like, boy, I wish I would actually sort of know what the mean difference is between those two. No problem. You just take that R, you convert it to a D, and then you can talk about that. In general, it should give you a general estimate for sort of standard deviation difference between those groups. So again, this is just recognizing that we can work back and forth between statistics, depending on sort of what serves us best in terms of interpretation. Other thing we can do with R is we can go through and square that R. What this is going to do is it's going to give us a different type of effect. Well, we can interpret that squared value of my Pearson correlation as the proportion of variability in Y shared with variability in X. Okay. We'll sometimes talk about this proportion variability in Y attributable to X. That kind of has some causal language. I don't mind it. People would get maybe some people get worked up about that a little bit, but so we're not saying that X causes Y. We're just saying it's sort of kind of accounts for it in the general sort of predictive sense. But again, if we're thinking about this as overlapping concentric circles, right? Like how much is shared there? Okay. So if I have an R of 0.5 and I square that, I'm saying 25% of the variability in Y is shared with variability in X. So there's a relation there. And so again, if I take 1, 3, and 5, and square those, I get 0.01, 0.09, and 0.25. This just gives me a different way of thinking and conceptualizing what's happening with these data. People seeing how we can kind of move back and forth and use these and sort of shape this to kind of different interpretations and ways that start to become sort of meaningful and persuasive in terms of the way that we're interpreting things. All right. So I want to talk about our assumptions of our correlation. Okay. So we're going through and we're gonna calculate our Pearson correlation. But in order to have confidence in my interpretations of the statistics that I've calculated as a metric of the actual population effect, I have to sort of make sure that certain assumptions are covered, okay? And most of this involves the assumption that the variables that I've sampled form some bivariate normal distribution, okay? Now, if I'm thinking about bivariate normal distribution of X and Y, we start to get into, I have to think about three-dimensional space here, okay? And what we've got here is if I think about just the distribution of X, I can picture that on a two-dimensional plane where I've just got X, Y, and then kind of sort of my two-dimensional curve there, right? Just the screening that we've done sort of up to this point, right? But if I'm looking at the joint distribution of X and Y, this bivariate normal distribution, now I need to get in three-dimensional space, okay? So everybody look at me. Do this, do this. I've got an X and Y axis, right? Throw out your middle finger and sort of do this. Okay, now we've got three-dimensional space right here, okay? We've got an estimate for X, value of X here, a value of Y here, and then where do those values pile up in my distribution? Gives me some three-dimensional sort of cone shaped something along these lines, okay? And this is what we start to, this is some of the complexity. And then if we were to go into three variables, now all of a sudden we're getting into multi-dimensional space and that becomes hard to visualize for us as three-dimensional beings. You know, the time and stuff, that's a whole fun different discussions. It's like podcast from here to Idaho. So, but this is a sort of maybe a graphical representation of what this would look like, okay? And so what we're concerned about with our correlations is we want to see that the marginal distribution of X and the marginal distribution of Y is normal. We're talking about the marginal distribution. This is me, Jack, this is just you saying, what's the distribution of X? Is that normal? Just looking at my sort of histogram. What's the distribution of Y? Is that normal? We want to make sure for bivariate normal distribution that X is normal and Y is normal, or sort of reasonably so, okay? We've already done this. This isn't anything weird that we need to think about, okay? But the thing that we do have to start thinking about is there's also the assumption of the conditional distribution of X and Y, okay? This is a new concept. The conditional distribution of X and Y says if we're looking at the conditional distribution of X, this is saying that the distribution of X values for any given value of Y is going to be normal, okay? So this isn't just looking at all our X's. This is saying if I look at the distribution of X for all corresponding to all Y values of 0, I would still see a normal distribution there, okay? And if I'm looking at my bivariate normal distribution, what I was essentially doing is I'm saying, okay, we're saying for all about Y values of -1, if I slice this distribution here, what would I see? Would I see a normal distribution? And here we're seeing a normal distribution here. So if I take my data set and I only look at Y values of -1 and restrict my data set to that, and then look at my X values that correspond to Y's of -1, what's the distribution of that? Okay. And what I would then do is say the distribution of X values for all Y values. And if I have truly continuous data, there's an infinite number of Y values and an infinite number of distributions. I would want to see them all roughly be normal in this way, okay? Same thing, if I'm looking at the conditional distribution of Y for values of X, what I'm going to do is I'm going to say, okay, for X equals 0, what do the Y values look like? Again, I'm taking this distribution, I'm slicing it, right? And if I were to look at the cross-section of that for Y or for X equal to 0, we're seeing sort of still a normal distribution, sort of a bell-shaped curve with this, okay? Now, again, with truly continuous data, there are an infinite number of X values that X can take on. And so for each one of those values, what I would do is I would look at the distribution of Y's, and what I would hope is that each one of those are sort of continuing. Or continuing. Okay. People kind of getting sort of this idea of conditional distributions and what's happening here. It can take a while to kind of wrap your head around, but sort of like just sort of be aware that these are what we're looking at. Also, sort of notice here for this asterisk. For regression, this is the only conditional distribution we have for regression. We don't have a conditional distribution for an assumption of the conditional distribution of X, because there are no distributional assumptions of X in a regression model technically. There become some because we violate other things. But again, technically, for regression, we are only interested in the conditional distribution of Y. Okay. Our X values can have any type of distribution they want, so long as I'm running a fixed effects regression. But we don't ever do that, so then that relates to other things. But so to note that, so these are the assumptions for correlation, where we're assuming a bivariate normal distribution, where we have distribution of Y, marginal distribution of Y is normal, marginal distribution of X is normal. Also, the conditional distribution of X is normal for any Y, conditional distribution of Y is normal for any of X. So we don't need to worry about this for regression or for regression either. But we'll get into that when we get into sort of assumptions of regression. Questions about this? All right. Bonus. Someone tell me again, sort of here, 3-dimensional space, throw it up here. What would the shape of the distribution, the bivariate distribution be for X and Y under a null model? Okay. Here we're seeing a relation between X and Y. What would this look like? What would this look like if the null were true, if X is unrelated to Y? What do you think, William? Flat. Not quite flat. Okay. I mean, so we're still going to have in 3-dimensional space because we're going to expect things to pile up. What might this look like? So here we have kind of a fin shaped looking, this sort of indicating some linear relation. Under the null model, what would this look like?
Just like a mound instead of just, yeah.
Just a mound, right? So here we're seeing sort of this fin is indicating sort of a direction of this. These are kind of lining up here. Under the null model, we would expect, so basically if I just took a pail of sand, sort of poured it down, sort of like down, it would just sort of flow out in all directions. That's what our sort of bivariate normal distribution would look like under the null model. Okay. So again, thinking about this as sort of values of X and Y, standing on sort of my 2-dimensional plane, and then sort of the frequency coming up in that 3rd dimension there. So getting your Pearson correlations in SPSS, easy peasy, right? Sort of basically analyze, correlate, bivariate. So here's what you're getting. Here's the table we're getting here. We're seeing a Pearson correlation of PDSC and social support of negative 0.274, asterisk. We've got a p-value that's less than 0.001. Pretty easy, straightforward. They're getting these out of SPSS. Stata, here's the command, PW core, variable, and then just ask for your p-value at the end, and it's just going to give you the same thing. Pretty easy to call up. All right. So we've covered correlations, okay? And what we would typically do with these correlations is we just like kind of look at the correlation, admire the correlation, interpret the correlation, move on, okay? But there are other types of things that we can do with these correlations, okay? One thing that we could do is we could compare independent correlations, okay? And in this situation, what we would do is maybe say, all right, here's the correlation between X and Y in this group. What's my first group getting?
Oh, wait,
What's that?
sorry.
I said, here's the correlation between X and Y in my first group. What's my first group? What's that?
Age.
Age, or
Wait, sorry, what is?
so I just so some group. Who am I talking about? Who's a population that I'm interested in?
Oh, graduate students.
Okay, here's the correlation between X and Y and graduate students. Okay, and then here is the correlation between X and Y in undergraduates. Okay, and let's say this is the sort of correlation between extroversion and time studying or something like that. I don't know, right? What we could do if we've got an estimate of an association in two different populations, what we can do is we can go through and compare those two. Okay. So in this situation, my null model is that the population correlation in so my first or the correlation of the population in my population 1 minus the correlation in population 2 is equal to 0. What we're saying is just these population correlations are equivalent to one another. My alternative model is that correlation, if I take the correlation in population 1, subtract from the correlation in population 2, I get some non-zero value. It means that they're not the same, they're different, right? What am I essentially asking? What kind of question am I asking with this? I'm saying the relation between X and Y differs in this group versus that group. What am I essentially talking about?
I don't know how to phrase it, but essentially, is this particularly relevant to one group? Like
Okay,
a
so
thing of like
kinda
a
you can
control
ask- yeah,
situation?
Yeah, you can kind of ask that. What statistically, what question am I asking?
Or getting back at moderation.
Yeah, it's kind of like a discount moderation, right? Like I'm looking at correlation in this group and the correlation in this group. Essentially, what I'm saying is this population moderate the strength of this association, right? Now, would I recommend you run a moderation analysis by comparing correlations across two groups? No, I would not. There are better ways to go through and do this. But if you had, let's say, pre-existing data, right, Cindy, let's say you've written a paper where you've got correlation between these two measures in this group and a correlation between these two measures in this other group, and you just want to compare those correlations and see if there were evidence of that they were different, you very much do that. And that might be the basis of saying, hey, maybe gender or cultural background, like something like that might serve as a moderator of the strength of this association, right? So you're exactly right. It's just a moderation question. It's just a different way of going about it. Okay. So again, we can do this with just based on observed correlations. Problem is that the distribution of the difference in correlation starts to become complex. Okay. If I take the population correlation 1, population correlation 2, and I just do this again and again and again and again and again, the distribution of that is hard to describe because it doesn't play nice with stuff, right? So what we can do though, sort of people smarter than me figured out what we can do is we can take those correlations and we can transform them into z-scores. And if we take those correlations, transform into z's, now we get a distribution that sort of makes a little bit more sense, plays nice. Okay. So if I'm transforming correlation with Fisher's R to Z, what I'm getting at the end of this is what we'll call R prime. Okay, and R prime is just 0.5 times the natural log of the absolute value, 1 plus your correlation over 1 minus your correlation. Okay. So if I go through and I plug my correlation, let's say I've got a correlation of 0.3, I plug it into this equation, what I get is R prime, that's my Fisher R to Z. Okay. And what's nice is what we know is that we know what the distribution of R prime is. We know that this is approximately normal around rho prime, which is going to be the population correlation. If I Fisher R to Z, the population correlation, okay. And my standard error for this is going to be 1 over the square root of n minus 3. Okay. And if I have a point estimate and I have a standard error, what can I get with that? You can get a test statistic, right? So what I would do is I go through and I take my correlations here, I transform them into Z in R prime, which is Fisher's R to Z, get my standard error here. And now what I can do is I can compare these using a Z statistic with R prime. Okay. So what I'm doing here, if I want to compare two independent coefficients, right? This is correlation of X and Y in this group and correlation of X and Y in this group. What I can do is I can take the correlation in group 1, turn it into R prime, get the correlation of R2, turn that into R2 prime, subtract those two values, and then take this all over the square root of 1 over and the first group minus 3 plus 1 over and the second group minus 3. Someone looking at this, what does this formula look very much like? From last semester. What do you think, Catherine? Yeah, it's just the independent sample t-test, right? I have sort of difference between my means over variability in my first group, variability in my second group. It's just a t-test formula here. It's just what we're doing is we're just taking, instead of using mean values, we're just using correlations. That's what I'm comparing those two. This is all essentially an independent sample t-test, except I'm just using correlations instead of means. See what we've got going on here.
Is there any specific reason we're subtracting 3 from
What's that?
like the sample sizes while we're subtracting 3?
That's just sort of, I don't know, math, that's statistics, yeah,
I
yeah.
figured, but
Yeah, so for Fisher's hard is other questions conceptually with what we're doing with this. And then what we would just do is we would evaluate this, see statistics we get with it against our Z scores, sort of p values, and like we do here. Most of you will do this by hand. If you are a SATA user, this CORTESTI, you have to sort of download this, but you just go through and use that command to go through and do this sort of space. And do it by hand, but you can use this to start your work. So, but again, sort of a sort of benefit of sort of different programs. All right. So this first go around, the first procedure was we're testing correlations that have been like pulled from two like discrete populations, two different groups, right? But the other thing that we can do, and this starts to get into some stuff, so going back to some of the meal papers that we read, you know, our null model, standard null model is that sort of rho is equal to 0, right? And we're testing whether or not something is different than 0, right? But we don't have to test against 0. We can test against whatever we want, right? If there was a situation where you said, Catherine, that the relation between say diabetes diagnosis and functioning in older adults is equal to a magnitude of 0.3, right? You can test against that, right? It doesn't have to be, is it 0, is it anything? If you had a strong theoretical sort of model-based reason to say, I'm saying that this is going to be larger than 0.3, go through, let's test this, right? And so here what we're doing is we're saying our null model is that rho is equal to some reference value, some R value, okay? Our null model, again, is that it's not equal to that, okay? So it's not like this is necessarily sort of giving us a sort of a better, like sort of, if my sample size is big enough, it will never equal exactly R, it'll be something bigger or smaller, right? But what we can start to do if we wanted to is start to get very specific about sort of our test. It's not just, oh, it's different than 0. It's equal to this one or higher, right? Hal does a nice job. He sort of questions the utility of this, right? But I don't know. I think if we've got working in an area where you've got lots and lots of information, you could say like sort of, I'm saying that let's say, Jayla, you're working with a sort of experimental thing. You're saying like, I'm saying if we introduce this manipulation, it can be correlated with the outcome to some degree that's sort of larger than what we would expect sort of based on meta-analysis. Let's say meta-analysis is saying that sort of relation between X and Y is equal to 0.3. I'm saying with this manipulation, it's going to push it harder, a lot larger. And so what we're going to do is we're going to do that. We're going to test the correlation against 0.3. And what I'm hoping is to reject the null that it's bigger than 0.3, right? You could set up a situation like this. This would actually be like, if I was reviewing a paper, someone did this, I would be super jazzed. I mean, that's super clever and cool, right? Calculating this is easy though. What we would just do is take whatever your observed correlation is. Sure, R to Z that, just turn that to R prime, and then whatever your expected value under the null was. Turn that into sort of rho prime. Take that difference, divided by the square root of 1 over n minus 3, and now you've got a Z statistic that you can go through and test. What does this look like? Where have we seen something that very much looks like that formula previously? What do you think?
Is it like the Z-test formula?
Z-test, yeah, it's similar to what specific Z or what specific T does that look like?
Like single sample
Yeah,
T-test?
it's just a single sample T-test formula, right? We just have our value, our observed value minus our reference value over standard error, right? This is just basically what this is. This is just a single sample T, except we're just using correlation values. Okay. So again, wanting you to start thinking about it, like looking at these formula and thinking about like, where have I seen this before? What is this like? Helping you sort of develop a sort of a conceptual understanding of what we're doing with this in ways that'll help you use this flexibly. Questions about this? Yeah.
If it's some value other than R, does direction matter, or is that just kind of up for interpretation?
R can be sort of like whatever you want it to be. If it's positive, it'll
Yeah.
be lots bigger, and if it's negative, it'll be negative, or it'll be smaller. Yeah. So yeah, absolute value doesn't. I wouldn't say like R equal to negative 0.3. That's that's just the valence is often arbitrary and sort of just depending on how we scale our stuff. So all right. Last thing that we can go through and do is sometimes, so in the first situation, we've got a deal where we have a correlation of X and Y in group A, correlation of X and Y in group B. We want to see if they're different. It's basically an independent sample t-test with correlations, right? The second scenario, we've got some observed correlation. I want to test it against something that's not zero, right? I've basically got like a single sample T situation, okay? What we can also do, and this is where I've used this with psychometric papers, right? Let's say that I'm looking at trying to build evidence for convergent discriminant validity, right? And I'm saying that sort of this measure that I've created should correlate more strongly with this existing construct than with that construct, right? It's clinical psychology, so everything's going to be related to everything. So I'm just not like, oh, there's a significant association, doesn't tell me much of anything, right? But I'm saying that this measure, if I've captured what I have intended to capture, it should be correlated more strongly with this outcome relative to this outcome. And with this, if that's what happens, then I can make an argument for evidence for convergent discriminant validity within sort of the context of this paper. Okay. People kind of seeing what I'm sort of getting at here. Okay. So Jack, help me out with this, man. Like you've got a measure, what do you got a measure of?
ADHD.
ADHD. Okay. And for you, ADHD should be stronger with a measure of what than a measure of what?
What are you asking?
So let's say I've got a measure of ADHD, right? And so that should be, ADHD should be more strongly related to what construct relative to what other construct? So let's say, so William, have some ideas?
Would it be like an ADHD measure should be more related to like a construct of like hyperactivity over depression?
Okay, I like that, right? Like, so let's say, sort of my measure of ADHD should be some more strongly associated with hyperactivity than, let's say, hopelessness. Not that if I have high levels of ADHD, that's going to be orthogonal to hopelessness. I would expect, because we know that sort of ADHD is comorbid with depression, and so it's kind of sort of carries along. But it should be more strongly and closely theoretically related to hyperactivity, which is a component of ADHD, than then I just measure the general distress measure or something like that. What I can do is I can set this up with my correlations, okay? And so what I'm saying here within this model, I'm looking at dependent correlations or correlated correlation coefficients. Is what I've got is I've got a system where I've got A, B, and C. Here's A, B, and C, right? And so I'm going to have this, this, here, here, and here. This is right. So I'm going to have three correlations, and all of these are collected within the same sample, and so they're all independent of one another, interdependent on one another, right? What I'm saying here is I'm saying that the difference in the population coefficients with the correlation of X and Y and X and Z is equal to 0. There's no difference in these correlations. Okay? I'm saying that this. Something like that. Okay? So what I'm saying here is that X and Y are correlated 0.6, X and Z are correlated 0.4, and then Y and Z 0.3. So we've got dependency across those measures. Okay. And so my null model here is that the correlation between X and Y and X and Z are equal to one another. Okay. In a population. And so my alternative model is that they're not. Now, so the issue that comes up with this is that can I just Fisher R to Z these and then compare these two? No, I can't, right? Because these are not correlations in different populations. These are different correlations within the same population, and they are dependent on this. And so when we're going through and calculating this, what we need to do is we need to determine to account for not only the magnitude of this correlation and this correlation, which we're trying to test against, the magnitude of the correlation of that Y and Z starts to become critically important in sort of strength of evidence for differences in these things. Okay, and so our formula that we need to use needs to go through and take this into account. We can also use sort of this dependency to start looking at the correlation of X and Y at time 1 with the correlation of X and Y at time 2. Right? If we're thinking that the change in time is going to change the nature of the association between X and Y at time 1 and time 2, we can also use this same type of model to capture that. Okay. Now, the statistical procedures for this are going to be a little bit more complicated because there's multiple factors that we need to go through and account for. But in your syllabus, you've got tests outlined in Howell. Okay. Steiger does some stuff, and then Meng does some stuff as well. They're all working with procedures for going through and testing correlated correlation coefficients. I like Meng because Meng does a little bit more. It goes through and starts to expand on running and testing correlations among like a set of correlations, seeing if there are differences, not just in pairwise coefficients, but sort of sets of coefficients, and doing some cool stuff around that. Basically kind of like a one-way ANOVA, except with correlations as opposed to means. Some really cool stuff and stuff that I found to be helpful in sort of navigating certain types of projects. So whatever sort of assignments, have you go through and take a look at that and go through and sort of build some calculators around that. Questions about correlated correlation coefficients? Okay, cool. Finish up with confidence intervals for your effect sizes. Because the confidence bounds for correlations, or excuse me, the distribution of correlation coefficients, we can start to sort of use Fisher's R to Z to sort of make those more manageable. Helps us out a little bit before we had to use Steiger and that calculator to go through and get non-centrality parameters. Here, we don't necessarily need to do that. But we do need to do some, just like we did before, some forward translation and back translation with stuff. So for calculating the confidence interval around a correlation coefficient, what we need to do is, again, first run that Fisher R to Z. So take R, turn it into R prime, and then calculate a confidence interval with my Z score for whatever confidence level I'm going to use, times 1 over n minus 3. That's my standard error estimate, right? So if I wanted to run a 95% confidence interval, what would my Z score be for a 95% confidence interval? Remember, Charlotte?
1.96.
1.96, right? If I wanted a 99% confidence interval, it's going to be 2.58, right? So it's just your Z score times this, and then sort of running that. What this is going to give you, okay, this starts to get a little tricky. This is where it gets tricky. This is going to give you a 95% constant, 95% confidence interval for rho prime lower and rho prime upper. But is rho prime lower and rho prime upper what we want to get? No, we want correlations. So what we need after we've gone through and we've gotten the sort of upper and lower confidence bound for R prime, what we then need to do is back translate those limits into Pearson correlations, which is not terribly difficult. It's just taking base E times 2 to R prime minus 1 over 1 base E to 2 times rho prime. You're just back translating sort of Fisher's R to Z with this. Okay. But if you do this, it will go back through and give you then a confidence bound around sort of lower and upper. So again, sort of with each of these, anytime you're saying rho prime, so the issue is I have R. The problem is the R distribution, the sampling distribution of R gets funky sometimes. So I can't work with R directly. What I can do though is I can take R and I can change it to R prime using Fisher's R to Z. R prime has a nice and orderly sampling distribution that I can work with. So what I do is I take R, translate it into R prime, run some calculations, get my upper and lower limit for R prime, but then I got to back translate that back into R's that I know and like and can use and interpret. And that's what this is doing. Okay. So not dissimilar. Remember when we were hand calculating confidence bounds around D last semester? And we can't do that directly with D. But what we can do is we can get non-centrality parameters, and we can take those non-centrality parameters, turn those into upper and lower differences, upper and lower limits, and then back translate those into D values. Same thing that you're doing here. You can do this in SPSS, get confidence bounds for your correlations. So here's the commands you kind of work through, and here you've got your correlation between sort of CAPS and MSPSS using point estimate, number of observations, upper and lower limit. So the same thing here. So you can do this in full data with, we often don't calculate confidence bounds around correlations. We should. I almost always like what I'll do is I'll go through it, maybe have like my correlation matrix and then have confidence bounds in the off diagonal or something like that. Starts to become really, really useful in sort of communicating precision of our estimates. In Stata, you can use these different commands CI2 and CII2. Just download those, pop those in, so it makes it easy enough there. All right, we'll finish with power analysis stuff here. Again, in G power, starts to become really easy to go through and sort of determine the sample that you'll need to identify adequately power your test of a given correlation. What you're going to do in G power, you're going to go through and select exact, and then you're going to say correlation bivariate normal a priori two-tailed test. You're saying I want to see how many people do I need to reliably identify, adequately power my study to detect a correlation of 0.3, alpha 0.05, power is 0.8. My null correlation is 0 because that's usually the model we're testing against. I go through and I calculate this and tell me I need 84 people to reasonably detect, have reasonable power to detect a population estimate of 0.3. That seems, that's easy, straightforward. All right. We about made it through everything. But we will pick up sort of this last section on, so we're talking about some point by serial P coefficients and stuff like that. When we regroup next Wednesday. Questions about the class, where we're going, anything up to this point? Okay. All right. I am happy to be back. I hope you